Hello. The CP transformation of scalar fields almost always involves their complex conjugation. In this paper also, the CP transformation of several flavons corresponds to their complex conjugation. Besides CP, other group generators utilized in this paper also involves complex conjugation. Since the conjugation is used extensively in this paper, I have decided to make this video to explain clearly how it is handled. Given a set of scalar fields transforming under a flavor group, we may introduce complex conjugation as the CP transformation. The introduction of complex conjugation leads to several complications and inconsistencies. The CP transformation defined in a consistent way is called the generalized CP. The generalized CP has been studied extensively in the literature. In this video, I will often use this paper by Holtersen, Littner, and Schmidt as the reference. In this paper, the authors studied generalized CP in a very comprehensive way. Here, I will not go to all the details. Rather, I will use a few simple examples to explain the basic concepts and then move on to explain the approach followed in my paper to handle complex conjugation. My first example involves the group S4. So I have multiplied phi with the components phi1, phi2, phi3. This is a real irrep, a real triplet, and I consider the tensor product expansion 3 cross 3 is 1 plus 2 plus 3 prime plus 3. With this multiplied phi, this tensor product expansion leads to a singlet, a doublet, and a triplet given here. In my paper, I have used two generators T and R to generate the group. Here you can see that the triplet is generated using bold T3 and R3. The matrices are given here, and the doublet is generated using the matrices bold omega 2 and bold sigma x. And here the bold omega 2 is a complex matrix, but keep in mind that 2 is in fact a real irrep. And finally, we have 3 prime, which is generated using T3 and minus R3. This is my setup. In the reference, the authors showed that to define generalized CP, we need to satisfy a consistency condition. For a rigorous definition of consistency condition, you may go through the reference. Here, I will explain this condition using this example. In this case, let us define a generalized CP as shown here. The triplet is conjugated, the singlet is conjugated, and the 3 prime is also conjugated. On the other hand, the doublet is conjugated and also multiplied with the matrix sigma x. So in general, generalized CP consists of complex conjugation accompanied with multiplication with a unitary matrix. Now let's see the significance of this particular definition. As I said earlier, phi is a real triplet. So under complex conjugation, phi remains invariant. And all these objects obtained from the tensor product, they must also remain invariant if phi is remaining invariant. Now let's see what happens with these multipliers obtained from phi under our definition of generalized CP. The singlet and the 3 prime are complex conjugated, and as you can see, these objects, the singlet and 3 prime, they are also real. So under complex conjugation, nothing happens to them, so it is consistent with the transformation of the triplet phi. On the other hand, the doublet is constructed with complex numbers. You can see that the first and the second terms are complex conjugate to each other. Therefore, under complex conjugation, these two components are exchanged. This is inconsistent with our original definition. Now, the multiplication with the matrix sigma x also exchanges the first and the second components of the doublet. Therefore, if you combine complex conjugation and multiplication with sigma x, then the total effect is that the doublet remains invariant, and hence this will be consistent with how the triplet phi transforms. So this simple example explains the consistency condition. Now I want to show you how the generators of the various multiplets transform under this definition of generalized CP. Because the triplet, the singlet and the 3 prime are simply complex conjugated, their generators remain unaffected. So this T3, R3, and then the trivial case, and then T3 and minus R3, all of them remain unchanged under complex conjugation. On the other hand, as we know, the doublet gets conjugated and multiplied with the matrix sigma x. Now look at the generators. The first generator is bold omega 2. So this gets conjugated and multiplied with sigma x. You have to multiply on both sides because these are matrices, and under this action, bold omega 2 remains unchanged. The same is the case with sigma x. So to conclude, all these group generators remain unchanged under our definition of generalized CP. This is summarized here. So the generator T goes to T and R goes to R. In the reference, the authors showed that non-trivial and consistent definition of generalized CP involves an outer automorphism. So an automorphism is a mapping, a structure preserving mapping of the group elements to themselves. In this simple example, we can see that each generator is mapped to itself. So this is a trivial automorphism. So this definition of generalized CP is trivial. It is not useful for us, and that can be seen from this tensor product. All these objects are real irreps. So by introducing a complex conjugation on the real irreps, we cannot expect to get anything non-trivial. In the next example, I will consider a case of an outer automorphism where we have a non-trivial definition of generalized CP. In this example also, I use the group S4. So we have phi, which is a triplet of S4. Besides S4, phi also transforms as shown here under a generator Z. Phi goes to omega phi, where omega is the complex cube root of unity. So this transformation makes phi into a complex error. So the group we are dealing with here is S4 cross Z3. The generators T and R generate S4, and the generator Z generate the group Z3. Now we have the tensor product expansion of the triplet with itself shown here. We get a singlet, doublet, and 3 prime. Um, Here I have used C to denote that these are complex errors. The errors on the RHS are given with a bar to indicate that they are the conjugate errors. So the errors in the RHS under the action of Z gets multiplied with the omega bar. Now the objects obtained from this tensor product expansion for the from the triplet phi are given here. So you have phi phi singlet, doublet, and 3 prime. The expressions of these objects are shown here. These are exactly like what we discussed in the previous example. So these objects transform under the generators as given here. The only difference in this case is that you have an omega bar which corresponds to the generator Z. Now let me talk about generalized CP. Just as in the previous example, we define generalized CP. So the triplet, singlet, and 3 prime, they simply get complex conjugated, while the doublet gets conjugated and multiplied with the matrix sigma x. And if you look carefully, you can see that this definition of generalized CP is consistent with how the original triplet phi and the objects obtained from them transform. Now let's see how the generators of various representations transform under this generalized CP. So since the definition is exactly as in the previous example, we can see that the generators T and R, they remain unaffected by GCP. On the other hand, the generator Z gets transformed. So we have the complex number omega, which when complex conjugated becomes omega bar, and this is true for all errors. So we can summarize these transformations as shown here. T going to T, R going to R, and Z going to Z square, because omega square is omega bar. So this is the transformation, and this is a non-trivial automorphism. In fact, it is an outer automorphism. And since it's an outer automorphism, the generalized CP defined in this way is non-trivial, and it is useful for model building. And finally, I show you how the generalized CP affect the tensor product expansion. So this is the original tensor product expansion that we discussed. So when we do the generalized CP, these errors transform. So 3C become 3C bar. Similarly, 1C bar become 1C, 2C bar become 2C, and so on. So this is an important point. So when we define generalized CP in a non-trivial way using an outer automorphism, always some of the irreducible representations, they change nature. In this case, the complex errors change to their conjugate errors. Another interesting example is the group A4. This group is not used in my paper, so I will not go to the details. But if you look at the reference, you can see how generalized CP can be consistently defined for A4. An interesting fact about the tensor product of the triplets of A4 is that it contains the singlet 1C and its complex conjugate 1C bar. Under the action of GCP, these representations 1C and 1C bar gets interchanged, even though the tensor product as a whole does not change under generalized CP. I will discuss one more example. we have the group S4 as we discussed earlier. But this time we complexify it using the group Z4 instead of Z3 in the earlier case. So under its generator Z, phi goes to I phi. So we have T and R which generate S4 and Z which generate the group Z4. So for the triplet 3C, the generators corresponds to bold T3, bold R3, and I. So as usual, the tensor product expansion is 3C cross 3Z, giving you one doublet, triplet prime. Unlike the previous example, the objects in the RHS are not complex errors here because you are squaring I, and I square is -1, which is a real number. So under the action of the generator Z, the objects in the RHS simply changes sign. So you have RHS going to minus of RHS under Z. Now the various objects obtained from the tensor product of phi with itself are shown here. Their expressions are as given in the previous example. You have a singlet, a doublet, and a triplet prime. And as I have written here, under T and R, their transformation rules are as in the previous examples, but under Z, all of them gets multiplied with a -1. Now let us define generalized CP. This is also as we discussed earlier. So the triplet and triplet prime simply gets conjugated. Similarly, the singlet also gets conjugated. On the other hand, doublet gets conjugated and multiplied with sigma x. And this transformation, this definition can be shown to be consistent. For the generators, the action of GCP is shown here. T and R remain invariant under GCP, while Z, which corresponds to I, gets conjugated under GCP. On the other hand, for the objects in the right hand side, the action of Z is simply multiplication with the -1. So GCP does not change it. So you have simply a -1 transforming into -1. These relationships can be summarized as shown here. So we have T and R remaining unchanged, while Z changes to Z cube. As you know, I cube is -I that we saw here, and then -1 cube is also -1 as we have here. So this is what happens, and this is a non-trivial automorphism, and this is also an outer automorphism. So this definition of GCP is non-trivial. Finally, here I show you the action of GCP on the tensor product. So the first equation is the tensor product of the complex representation 3Z with itself. So we get all these 1, 2, 3 prime and 3. On the other hand, when we take the conjugated representations, again the objects in the right hand side are exactly that we obtained earlier. So it looks like both of them are the same. However, if you look at how they are constructed from the triplet phi, we can see that, for example, this first object here, it is phi 1 minus, while this object here is phi star 1 minus. Both these objects transform in the same way. That's why in these two equations they appear the same, but their construction is different. We can show that the real and imaginary part of this phi 1 minus, which is this real part is just the sum and the imaginary part is I into the difference, these objects transform differently. The real part remains invariant under GCP, while the imaginary part changes sign. So this information is not obvious in these equations shown here. And that is and this is true for the other multiplets also. We have the doublet uh, splitting into real and imaginary parts, and the triplet prime also splitting into real and imaginary parts. More complicated cases of linear combinations appear in my paper. So the main point that I would like to convey using all these examples is that if we introduce generalized CP, several complications arise, such as one irreducible multiplet transforming to another, or new irreps being formed as a linear combination of the existing irreps. In my paper, I found it very difficult to keep track of all these complications. Therefore, I followed an approach which is slightly different from what we have been discussing now. Now, this approach is based on the results given in the reference. The authors showed that, let's say we have a group G, a flavor group G, and then we introduce GCP. Now, if you don't consider GCP as a separate thing, rather include GCP as a group transformation along with the group transformations in G, then you get a larger group. And this larger group is of the form G semi-direct product Zn. So we may call this group a flavor GCP group, because this group contains both the transformations in the flavor group as well as the GCP transformations. For simple cases, Zn is simply Z2, but it can be other larger cyclic groups also. So now let's say we have complex irrep phi of the group G, and then we introduce GCP and consider GCP and G as a single group, the larger group. Then in that larger group, phi and phi star together form a single irrep. And in fact, this irrep will be a real irrep, and its dimension will be twice the dimension of the original irrep phi. So if we have a complex triplet phi, then in the larger group G semi-direct product Zn, we will get a real irrep of dimension 6. Let me explain how I use this larger group in my construction. So consider the flavone chi in the paper, and this transforms as a 3' of S4. Also, under a generator ZL, chi gets multiplied with omega. Here L denotes charged lepton. So the group we are dealing here is S4 cross Z3. Now we have the tensor product of 3' with 3' as usual, and the various objects obtained from the tensor product of chi with itself are given here. The expressions of these objects are as we discussed previously. So we have a singlet, a doublet, and a triplet obtained from the tensor product. And we note that all these multiplets are complex irreps. Now, we also consider the tensor product of the conjugate of chi with itself. 3c prime bar cos 3c prime bar, we get singlet, doublet, and triplet prime. So that corresponds to chi star cross chi star, and we get these objects chi star 1c, chi star 2c, and chi star 3c prime. And these objects are defined as the complex conjugates of the objects obtained earlier. That is, this object is the complex conjugate of this, that is shown here. This object is the complex conjugate of this, so I've denoted it here, and like that. Finally, I consider tensor product of the conjugate of the representation with the original representation, that is chi star with chi. And in this case, objects in the right hand side, all of them are real irreps, because we have multiplication with omega bar and omega, both of them cancel with each other, and the expressions of all these things in the RHS are shown here. One thing to note is that in the case of chi cross chi or chi star cross chi star, the antisymmetric part vanishes, so we don't get 3. On the other hand, with chi star cross chi, we also obtain the representation 3 in the RHS. Now we define generalized CP, and its action on chi is simply defined as complex conjugation. Now, unlike in the previous examples, we don't consider generalized CP separately. With the introduction of complex conjugation as one of the group transformations, we obtain a larger group, which is this semi-direct product. In this case, originally we had S4 cross Z3. Now we get a semi-direct product with Z2. So what happens with our triplet chi? So you have chi and chi star forming a single erupt. This would be a 6-dimensional real erupt. And what are the generators of the group acting on it? So the generators should be 6 by 6 matrices, and they are shown here. So for generator T, you have this block diagonal matrix. So this is a 3 by 3 T3, and then T3 star block in this block diagonal form. T3 star is T3, so you get this. Similarly, for the generator R, we get this 6 by 6 matrix shown here. Now for the generator ZL, we have the block omega and then the conjugate block omega star. Unlike T and R, these two are different. So you have this omega and omega bar. Finally, we also have the action of GCP. In the paper, I use C sigma to denote the generator of generalized CP. And the action of generalized CP, as I said, is the complex conjugation. So that means chi goes to chi star and chi star goes to chi. So that will have this block diagonal form where this 1 and 1, they are 3 by 3 identity matrices. So we have this 6 by 6 matrix representing generalized CP. Now all these 4 generators, T, R, ZL, and C sigma, they generate the group S4 cross Z3 cross semi-direct product Z2. Now let me consider the tensor product of the multiplet with itself. Now chi is no longer an erupt. Chi and chi star form a single 6-dimensional real erupt. So the tensor product is chi chi star cross chi chi star. And we get various objects here. And in this expansion, I have omitted the anti-symmetric part. So this only corresponds to the symmetric part. These objects, chi star chi 1, chi star chi 2, chi star chi 3 prime, and chi star chi 3, they are nothing but the objects I obtained here. That is these 4 objects. Okay, and the 5th one that you can see here, it's a doublet. So you have chi chi 1c bar and then chi chi 1c bar star. And what is this object? It is nothing but this object and its complex conjugate this. So these 2 objects form a single erupt in that expansion. Similarly, this doublet and its conjugate, this one, it will form 4-dimensional erupt. So that is shown here. Finally, you have this 6-dimensional erupt, which is nothing but this object and its complex conjugate this. All these erupts that I obtain in the RHS, all of them are real erupts of the larger group. And as you can see, I have used complex numbers to represent them, but they're all real erupts. This all may look a bit complicated, but the advantage of this approach is that now I don't have to consider generalized CP as something separate from the flavor group. So these other complications like one Arab going to another, or obtaining new Arabs as linear combinations, all these problems just go away. Finally, I want to discuss the notation adopted in the paper. The first point is all scalar multiplets in the paper are real Arabs, even though I often express them as complex multiplets of half the dimension. This is for convenience and brevity. The second point is the complex multiplets in the LHS of tensor products are treated as real Arabs of twice the dimension. So if I write chi cross chi in the paper, what it mean is chi chi star cross chi chi star. So I'll show you that equation. Um, Please have a look at equation number 21. So we have chi cross chi. This is in fact chi chi star cross chi chi star. So what do we obtain from this tensor product that we showed here? We have 1, 2, 3, 4, 5, 6, 7 Arabs in the tensor product, and these 7 Arabs are shown here: 1, 2, 3, 4, 5, 6, 7 Arabs. So this equation is exactly equation number 21. The next point is, in the RHS, I often express the real Arabs as complex multiplets of half the dimension for convenience and brevity. Let me explain this with our example. So we have this two-dimensional real Arab. So chi chi 1c bar and chi chi 1c bar star. Now the second component is the complex conjugate of the first. So this real Arab, real doublet, can simply be expressed using just one complex component. So this is what I do. This doublet is represented as chi square delta here in the paper, and I can show you its definition. We have it here. So chi 1 square plus chi 2 square plus chi 3 square. This chi 1 square plus chi 2 square plus chi 3 square is nothing but chi chi 1c bar. So I am not writing the second component. I adopt this notation. This is also for brevity and convenience. And the final point is, this is an important point, complex conjugation is utilized in various group transformations beyond generalized CP. So let's look at this object, chi star chi 2. This is a real doublet, okay, and its expression is given here. Right? It has two components, and the two components are complex conjugate to each other. So here also you may just use the first complex component to represent the real doublet. That is exactly what I do. Look at the definition given in the paper here. Chi square alpha, that is this object is this. So this is in fact a doublet. When we do this, we have to be careful, because here the complex conjugation does not correspond to generalized CP. So let me explain that. The generators acting on this doublet are given here. T is this, R is this, and ZL is trivial. The generalized CP is trivial. So if you simply take the first component, T corresponds to multiplication with omega, and R corresponds to complex conjugation, because R is the exchange of the first and second components. Because these components are complex conjugate to each other, R just corresponds to conjugation. This is what I have written here. So T is multiplication with omega, R is complex conjugation, ZL and C sigma are trivial. In this example, the action of R, which has nothing to do with generalized CP, is complex conjugation. And in the paper, I also introduce some other generators. These generators also involve complex conjugation. Now you may have look at this table. In the left side of the table, you see the various multiplets obtained from the tensor products of the flavons appearing in the model. And then here we have the various generators of the group. And C sigma is the generalized CP. And as you can see, complex conjugation appears as a part of the generalized CP. But beyond that, you can see complex conjugation appearing here, here, like that, and in all these places. So this is the point I'm making. So throughout the paper, complex conjugation appears as a part of the flavor GCP group, not only for the GCP part, but also for the flavor transformations as well. This use of complex conjugation helps me to define various generators in a more convenient way. So that is why I do this. I hope that this video has given you enough information about how I handle complex conjugation in this paper. And I hope that this explanation will make your reading of the paper a little easier. Thank you very much. I will see you again in the next video.